Pueblo Viejo gold deposit in the Dominican Republic, and providing you with the evidence that I feel backs up a shallow water volcanogenic massive sulfide model for this early Cretaceous deposit. Brought with me geologic maps of Pueblo Viejo and the Pueblo Viejo district. They're laid out here that we can talk about them, have a look after the session. Particularly giving a talk here at the School of Mines with plenty of students present. You'll see that my emphasis through the talk is on geologic mapping. My first job in the industry was with Anaconda Copper, and we learned to map on levels to distinguish rock unit from structure, from alteration and mineralization, and to work actually on levels of mylar that then we could pile later on. The advantage of that method, which I still use today, is that it forces us when we're in the field and it's hot or raining to make all of those important observations to distinguish rock units from hydrothermal alteration and to get everything recorded on the outcrop rather than trying to remember later on after you're back at the office of the hotel. So here's the organization of what I'll be talking about today. Pueblo Viejo is the 5th largest gold mine in the world, producing just under 1 million ounces a year. I'll be talking about the regional geologic settings for deposits forming during the early Cretaceous in a Pholitic intraoceanic island arc. We'll take a quick look at the genetic models and how radically they
No complaints about the pie. It must have been better than you
Then
thought.
we'll move on to the local geologic
Average,
evidence for a
not as
volcanic
good as
Better than you
east of
thought.
volcanic
not as good as
sulfide mineralization. The
Costco.
now has been pretty much resolved. The ore deposits are early Cretaceous. A couple of references coming up with about 112 million years for dates on mineralization. Calc-alkaline intrusions are present in the district, but they turn out to be much younger. Late Cretaceous, around 88 million years. There's still quite a bit of controversy about the models. I think I should acknowledge that right up front. So we'll look at and discuss the aeromagnetic images and talk a bit about porphyry potential. And then finally, I'll end up with where I think we ought to be looking for the next Pueblo Viejo. So there it is, the world's 5th largest gold mine. For the past 10 years, it's been averaging very close to 1 million ounces of gold per year at an average open pit grade of 4.5 grams per ton. Joint venture of Barrick Gold 60% and Newmont at 40%. We're looking north at the Monte Negro pit. I like putting this slide up just to let folks know that the mining companies don't run away with all the money. There's the estimate of gross revenue for the life of the mine, an estimate made back in 2012 when metal prices were quite a bit less than they are now. Importantly though, half of the profits, half of the cash thrown off by the sale of those metals goes to the government of the Dominican Republic, and about half goes to the joint venture of the companies that put up the money to pay that $5.7 billion capital cost. So it goes about 50-50, the miners, and 50-50 the government, and this is pretty typical for big operations today. The source of that information is the 43101 report prepared in 2012. Here are those published genetic models. The top 2 are porphyry models. Dick Silito's 2006 paper proposing a laramide porphyry link for Pueblo Viejo. And then a later paper in 2017 by Lazard Carreau, his PhD thesis, after the rhenium osmium dating had been done on mineralization. But sticking with the porphyry model, There are also a couple of DMS related models been published. The first one by Silito et al. In 1996. And I would put myself in that DMS camp now. And then finally, we have the epithermal deposit models. The first really thorough paper done on Pueblo Viejo by Kessler et al. In 1981, when hot spring deposits were brand new, proposed it as an epithermal deposit, and that was picked up by Silito and Bonham in '84, and also by Russell and Kessler in 1991. And then finally, Silito has suggested in 2000 that it might be a unique deposit, a one-on type deposit, something that isn't repeated anywhere else. Now, forgive me, but all of these models can't be true. And I've been, as you can imagine, struggling with these models and trying to reconcile them with my own observations. My first trip to the deposit was in 1980, SEG sponsored field trip deposit. I came back in the late 1980s with a faculty grant from Fulbright Foundation, allowed me to spend some more time there. Then in the mid 90s, I was mapping the pits at 2000 scale from Mount Isa to mines to prepare to bid. And that was probably one of the most important experiences of my career, the chance to map the pits in detail, no time constraints. Since then, I worked in the area surrounding the deposit, mapping regionally for junior companies that had the concessions surrounding the mine. And then for the past 20 years, I've just been going back myself whenever I get the chance, hopefully in January, February, when the weather's good, and finishing off the mapping of the district. So I finally got everything drawn together. There's a paper here. You're welcome to take a copy. It's there on the table up front. 2023 is when I tried to pull all of this stuff together. I'm also happy to send it to you via PDF. Okay, well, let's start having a look. We're in an intraoceanic island arc. I've shown that in green on the top figure. It stretches across the northern margin of the Caribbean plate. It was actually formed in the early Cretaceous off in the Pacific. But as the North and South America drifted apart, Pangea broke up, that island arc eventually crashed into the extended southern margin of continental crust, represented by the Bahamas. So we have an early Cretaceous island arc accreted to the southern margin of the North American continent. The little gray box in the Dominican Republic is enlarged in the below. So this map here covers this area of the arc. See the Pueblo Viejo deposit, and we're in an intraoceanic island arc in green, intruded by tholeiitic batholiths of tonalite composition. That island arc is overlain by carbonates, shallow marine to platform carbonates, and it's intruded by late Cretaceous calc-alkaline plutons. So now we're going to look a bit more closely at the Pueblo Viejo district. The green are our tholeiitic basalts and basaltic andesites. The yellow are tholeiitic as well, but they're dacitic composition. Lots of nice big quartz phenocrysts in these yellow dacites. They're overlain by a marginal marine, epiclastic, carbonaceous sedimentary section composed entirely of fragments of the eroded from this volcanic arc. We actually have terrestrial plant fossils in these carbonaceous sediments. And those in turn are overlain by a nearshore reef limestone called the Keel limestone of Aptian Albian age.
Carl, I'm sorry, for clarification, carbonaceous, you mean what?
Organically derived carbon.
Not as in carbonate rocks, but
That's right. Not as in carbonate. So these are carbonate rocks. These are carbonaceous sediments.
Thank you.
Now we're gonna take a look first at what I've labeled up here, Montenegro volcanic domes. Here's an outcrop from the north end of the Montenegro pit. This was where, on that 1980 SEC field trip, the Mara diatreme model was born. It seemed plausible, sitting on the margin of this big set of volcano sedimentary basin, that this coarsely fragmental basaltic andesite agglomerate was of pyroclastic origin and may have been the apron deposited after a big Mara explosion, which left the basin that was eventually filled by carbonaceous sediments. So now, this is a cross-section drawn by the mine geologist, but with my names, my interpretation of the rock units on it. But for morphology, here's the basalt andesite. Flat lower contents, flat lower contacts, here regular top contact, and overlaid by a coarsely fragmental, what I'm calling dome apron. That coarsely fragmental dome apron is entirely composed of fragments from the basaltic andesite. And the contact, as I'm about to show you, is sedimentary and conformable. These are not intrusions, at least not along their tops. The ore deposits are shown in red, and you can see a spatial relationship with the domes, and in gray are those carbonaceous volcaniclastic sediments. So let's walk down the pit wall here and have a look at this contact. We've seen what the fragmental apron looks like. And here's what the contact looks like, the upper contact of that basaltic andesite. It's massive basaltic andesite exposed here. We've got some offset along later faults, but the hammer, the head of the hammer is on the contact between the carbonaceous volcanogenic sediments and the massive basaltic andesite. So nowhere can you find any evidence for intrusion of that massive basaltic andesite into the volcanosedimentary section. And nowhere can you find any evidence of contact metamorphism by the andesite of the host of the surrounding sediments. Here's another picture from the same pit. These are the carbonaceous sediments. You can see them bedded subhorizontal. There is a coarsely fragmental apron deposited along the margins of the volcanic dome. And then the volcanic dome itself is massive basaltic andesite. So that's what I'm mapping in the pits. Of course, everything turns gray when it's mineralized. It can be tough to see these contents. Here's the model I'm thinking applies to these volcanic domes. Volcanic domes, by definition, going all the way back to the 1900s, are intrusive at depth, but breach the paleosurface and are eroded into the sedimentary section. So this is a volcanic dome of andesite composition being extruded into the crater of a volcano in the Lesser Antilles, the Soufriere volcano. You can even see down here in the box a little boat with a couple of figures headed towards the margin of the dome. I have to admit, I'm one of the guys in that boat. Our professor generously offered to stay on shore and take photographs and sent his two students off in this little glued together fiberglass boat over a lake that was already at 180 degrees Fahrenheit. You can imagine the heat, you can imagine the smell of sulfur, but what I most remember is how noisy it was. This dome is actively extruding. The crust is cool, solid, and it falls off as the dome extrudes, and fragments are constantly falling down the margin and down the base of the dome. That's what I think happened at Pueblo Viejo. We have volcanic domes, and interestingly enough, we have volcanic domes of two compositions, both basaltic andesite and dacite. So we're going to move from the Montenegro volcanic dome, a basaltic andesite one, down to the Moore volcanic dome. These are the two main pits, Montenegro and Moore. About 40 million ounces total mineral resources in terms of production and current resources. And again, what we see are bedded volcanosedimentary units, the carbonaceous section, a dome apron of coarse fragments, and I've zoomed in a little bit on this portion of it to show you how coarsely fragmental it is, and then a massive volcanic dome, this time of dacite composition. Has big quartz phenocrysts. We just had a look at the top of this dome. And again, this is a cross-section drawn by the mine geologists with my interpretation of what the rock units are. So this mushroom-shaped morphology of what I'm calling a buried volcanic dome is real. 300 kilometers of drilling in this deposit. So there's good control on these contacts. And here is the ore deposit at Moore. The pit, as you can see, works its way down and eventually hit the top of this dome, allowing you to look at that top contact. We're now going to look at this contact up here, which I labeled a volcanic dome root. So here, lower in the stratigraphic section is this dome, where we have its eroded top exposed. Up here, higher in the stratigraphic section, I'm going to show you the roots of the volcanic dome. So that at first blush feels contradictory. But what happens, in my view, is that this dome that is now buried, it intruded early. It's been buried by the volcanic sedimentary section, and then later domes have intruded and probably formed a mushroom-shaped body above that's now been eroded away. The domes become part of the volcanosedimentary section. They become part of the subsiding sedimentary basin. So here's that contact between the dacite porphyry, which has been dated about 111 million years, and the thinly bedded carbonaceous volcanosedimentary section, here tilted steeply near the contact with the dacite porphyry. Usually the carbonaceous sedimentary section is subhorizontal, but near this contact with the dacite porphyry, it's tilted as if the dacite porphyry had shouldered its way in. There's no displacement along this gully. There's no fault in this gully. And what you can see, if you ignore the color change for a minute, is that we can still see that sedimentary bedding on the right-hand side of the gully. We can still see this bedded volcanosedimentary section here. And what's happened is it's been baked by the intrusion of the dacite porphyry, which cuts across, as you can see in this close-up, cut across bedding. The geologist here is having a look at that. So here we are high in the section, looking at the intrusive root of a volcanic dome that's been eroded away. These are some thin sections and photomicrographs, and I have to acknowledge Jim Piper. If you ever need a photographer, this is the guy you gotta go to. He was really helpful in sorting this out, because we're looking at contact metamorphism of a previously altered and mineralized rock. These fragments here are full of porphyry. So those are volcanic fragments. I suspect they might have been glassy fragments that are filled with porphyry. Most of the black material is carbonaceous. And as we move from 40 meters away from the contact towards that contact, we gradually lose. There's the 40 meters away. This bottom one is 10 meters away from the contact. By 3 meters, we're picking up diopside and andalusite. And by the time we get to the contact, we've pretty much burnt off all of the organic carbon that was originally present. This is the most recent paper come out from 100th anniversary volume at CG. And you can see it has a couple of intrusive rocks here, the diorite dikes and an intrusive andesite, which if it's intrusive, I guess we call it diorite as well. But I'm using here the terms from Bonnadal 2020. This is a cross section through both Moore and Montenegro. My only change to this cross section would be to emphasize that the top contact is sedimentary, is conformable. There's no discussion about this being intrusive down here, but that dome cuts through to the paleosurface and is eroded, as shown on this cross section down here for my 2020. So these are the same domes that we have it shown here, but I believe that they made it all the way to the paleosurface. Okay, that's example of two domes, one basalt andesite, one dacite porphyry. I'm going to now move on to the evidence for VMS mineralization. We're going to look at this section of the carbonaceous sedimentary section just off the north end of the Moore volcanic dome. So these VMS layers are found very close to the margin of the dacite porphyry volcanic domes. We can all agree, I think, that they're stratabound. Here are a couple of photographs, stratabound, massive sulfide, bedded in that carbonaceous sedimentary section. The controversy has always been, of course, well, they could be replacement. Maybe they're not sediments, maybe they're not true beds. This carbonaceous sedimentary section itself is thinly bedded carbonaceous siltstone, carbonate cemented siltstone and sandstone, and then stratabound layers of massive sulfide. Some of the fine texture in this carbonaceous sedimentary unit, you can actually see what looked to me like just little layers of a sulfide mud deposited on that very shallow seafloor. Remember, we're in between the volcanic section and the shallow reef carbonate. We're at very shallow depths. This is not a deep water VMS by any means. These are pictures of massive sulfide beds that were exposed in the Moore pit, again, close to that intrusive contact with the dacite porphyry, exposed in 2018. You can see the massive sulfide beds. You can even see fragments of massive sulfide within the massive sulfide beds and within the carbonaceous sedimentary section. Here's a big fragment here of massive sulfide caught up in that carbonaceous sedimentary section. And that to me settles the argument over placement versus sedimentary origin of these layers. That's evidence that that a massive sulfide was eroded and deposited in the section with the bedded massive sulfide. I took GPS measurements of the location, and I was surprised to find when I got back and was reviewing my notes that these units that were exposed in 2018 were directly below the massive sulfides I've mapped in 1996, 1998. So we actually have stacked massive sulfides in that subsiding basin, in that carbonaceous volcano-sedimentary section. Stacked massive sulfide layers. Evidence that the basin is subsiding, the carbonaceous sediments are accumulating, the volcanic domes are intruding, and mineralization is ongoing all at the same time. I believe these beds that I've just shown you comply with the definition of VMS deposits, stratobound accumulations of sulfide minerals that precipitated at or near the seafloor in spatial, temporal, and genetic association. I'm by no means saying that all of the ore deposit is bedded. Most of it is disseminated, a lot of it is staining, that there are these true massive sulfide layers, massive sulfide beds preserved. As far as the age of the mineralization, I think that's been resolved now. We have rhenium osmium dates from two sources, Kirk et al. In 2014, and then my paper in 2015. Both agree very closely at 112 million years. This is isochron age on samples of sulfide from the ore deposit itself. These are model ages on samples of molybdenite, so a bit more precise, but not from the ore deposit. About a kilometer west of the ore deposit, but within the same alteration system. So 112 million years for the age of Pueblo Viejo. Now the volcanic domes I was showing you, they have this kind of distribution. Green are the basaltic andesites, yellow are the dacite porphyries. The ore deposits are here. And you can see kind of a northerly trend to the domes. There's also a northerly trend to the feeder faults that provided the hydrothermal conduits for mineralization. We have volcanic domes and hydrothermal alteration and mineralization taking advantage of the same high angle northerly striking feeder faults. I've brought the 1 to 15,000 scale maps for this map and for the next slide with me, because you really can't show a big map in a small publication. But there are 6,000 point observations that went into the construction of this map. A lot of field work by a lot of geologists over many decades. Here's the same area mapped at the same scale, but now we're looking at hydrothermal alteration. The previous one was the rock units. This paler green is what used to be called spilitization, simply seawater alteration of a subaqueously deposited largely basaltic andesite. Propylitic alteration is in darker green, where I see a lot of disseminated sulfides. I've added a stippled red pattern. Zones of intense silicification, which are focused on the volcanic domes, shown in orange, and then the advanced argillic alteration is shown in this yellow color. This orange line, which is a little bit hard to see, but you can follow my pointer around here. That's the extent of the lithocap as defined by Big Silico 2006. Interestingly enough, this is the limit in purple of the mining reserve. So although it encompasses all the existing pits, it by no means covers the entire alteration system. and by no means covers all the hydrothermal mineralization that's been discovered today. And this kind of mapping again goes back to Anaconda. I come back from the field and my boss would, I'd hand in my report on my field work and my boss would say, well, Carl, where's your map? And after a few months, it didn't take me long, I realized he didn't want to read anything I had to write. He wanted to see the map. And since then, I've got to admit, it's forced me to look closely. Whenever I've got my map with me, I'm looking more closely than I would otherwise. One of the things we were always taught to do is make sure you define the size of the alteration system. Walk out of hydrothermal alteration. How far do you have to go before you leave the hydrothermal system? Here's some cross sections. The top one is from my 2023 paper. The bottom one is from Lazard-Perot's 2017 PhD thesis. Excellent PhD thesis, by the way. There are two different scales. I should point that out. There's 1 kilometer on the lower one and 4 kilometers. So this whole section would fit on Mona over here. He unfortunately didn't have access to the mine. But the question is, and continues to be for many, is there a potential for a porphyry deposit here? So if you look at my section, and particularly the alteration sections, I don't have underlying intrusions with porphyry deposits associated. I have a big tonalite batholith, but I don't have, say, a series of calc-alkaline intrusions that might have driven a porphyry system. The Sard, on the other hand, has a tonalite intrusion here. He has a funnel-shaped phyllic zone above it, and then he has a lithocap above that, which is eroded here to the east. So this section would certainly say yes, there's good potential for more arguments in favor of a porphyry. Here's the aeromag, reduced to full aeromag map of Pueblo Viejo with the ore deposits, Montenegro and more. And this is, as I'm sure you all recognize, a typical aeromag signature for a porphyry system. Porphyry being coinciding with the magnetite destructive hydrothermal alteration, and indeed this could suggest a porphyry target at depth. There's a cross section, and of course silicose model that we would just place right in here underneath the ore deposits. Problem with geophysical cross sections is same as we have as field geologists. You give two geophysicists the same data and they'll generate different cross sections. And indeed, that's what's happened here. This is the same data, same geophysical data. There's the mag high, there are the ore deposits, and here's the cross section. So I plotted them one over the other. Tried to plot them at the same scale. There are the ore deposits. Here's the first section. There's the second section. And it's worthwhile recalling that these aren't true sections, they're pseudo sections, although they're drawn using the same data. The vertical dimension is not fixed. It wouldn't be hard to generate this kind of section from this same model here simply by extending the vertical dimension and clipping the data to only deal with this section here. So we have different interpretations even from the aeromag data. So what do you think? Do we drill for that underlying porphyry deposit? And Bob? Oh, okay, got two. All right. Barrick agrees with you. They've agreed to spend up to $10 million beginning in 2020 to test for a porphyry deposit under that lithocap. Here's the location of the cross section by Thoreau. And here from my own sampling, right in this area, are the drill holes where we found some molybdenite. So some of my own work can be used to argue for a porphyry target right here, immediately west of the pits. But wait a minute, that's not virgin ground. There's been a lot of drilling on that alleged lithocap already. Everton Resources drilled close to 40 holes and has these were the best intercepts. Barrick, when it got started with its joint venture, drilled it, let's see, 6 additional holes in 2021. And again, very, very weak mineralization. 10 more holes I haven't seen results yet for were drilled in 2023. So that's the test that's been done so far of the lithocap. And we're looking only at drill holes that were done outside of the immediate mine area. Mine has done its own drilling. So what happened? What did we learn? Well, I go back and I look at these drill holes, APV 41. Here's the core from deep in APV 31. APV 38, 11-38 right here. Here's the core from that tonalite interval deep in APV 38. My friends, these are the same rock. I don't mind calling it tonalite, that's fine. But if we're going to call this tonalite, then we have to call this tonalite over here too. What about the hydrothermal alteration? Well, let's look at the XRD results from 11-38, going right down this hole here. Presumably, we're going from sericite, phyllic alteration, through a bit of propylitic into potassic alteration, K-feldspar, biotite, magnetite, and into the intrusion, the tonalite intrusion. But when we look at the XRD results, these are all propylitic assembly. Fluorite, pyrite, epidote, calcite, and sericite shows up in pretty much all of them, right from the top to the bottom of the drill hole. So in summary, I'm not buying the cross section. I'm not buying the evidence for a porphyry type hydrothermal alteration system. Well, Carl, what about the perophyllite? If you send someone out with a handheld unit to look at the patterns they get for the rocks up here, they'll come back with plenty of perophyllite. There's plenty of perophyllite up here. But wait a minute, it's metamorphic perophyllite. It's a perophyllite schist. We can't count metamorphic perophyllite as advanced argillic alteration. Nor can we count metamorphic sericite or metamorphic fluorite as advanced as an alteration there. So I've mapped metamorphic recrystallization separately from hydrothermal alteration. I brought that map along, but here's a small version of it. All of this stippled area here are metamorphosed, are schists with this kind of texture. This is a perophyllite schist. These are perophyllite schists. Here's what those metamorphic rocks look like. We've got them exposed in the pits at the south end of Montenegro. Strongly metamorphosed unit here, thrust over the mineralized carbonaceous sedimentary section. So we actually see that contact well exposed. Then schists above weakly or incipiently metamorphosed carbonaceous units below. Move on to calc-alkaline dikes. I was very surprised to find out that these dikes that intrude the entire section in the Montenegro pit were calc-alkaline in composition. So I thought to myself, oh no, the porphyry model raises its head again. And, you know, I got to admit, if you see a calc-alkaline dike cutting right through your ore deposit, you got to wonder. Maybe it's a calc-alkaline intrusion below driving the whole system. So I sampled the calc-alkaline intrusion. I sampled the dikes that cut through the pits. There's Montenegro, there's more. And I got dates of 88.5 million years. 88.5 here and 88.45 over here. So indeed, those dikes are calc-alkaline. There's a big calc-alkaline intrusion here, but it's quite a bit younger than the 112 million year date on mineralization. So my recommendation is take care with cross sections from published models, mine included. You gotta do the mapping. You gotta do the mapping. You gotta trust your own observations, and you gotta build your own cross sections. Too often, if we go out with a model in mind, that's all we see. And we'll take those models and overlay them on our cross sections. And it's just a dangerous way to proceed. You got to do the field work. So here's kind of summing up my cross sections for the Montenegro deposit. The rock units for Montenegro, the hydrothermal alteration below it for Montenegro, the Moore deposit and Moore deposit alteration below it. Vein and disseminated gold, silver, but also copper and zinc mineralization. I put them in parentheses because neither copper nor zinc is currently being recovered from Pueblo Viejo. But copper was recovered for a while, and zinc gets up to about 1%, the higher grade portions of the ore deposit. They were deposited, most of the deposit is in the volcanosedimentary section, deposited at shallow depth. That's a shallow marine section overlain by carbonate, nearshore carbonates. Many of you, myself included, attended Thomas Monarchy's presentation on Friday here at the School of Mines. Here are some of the things he emphasized as important in building a big VMS deposit, a 50 million ton and above VMS deposit. Extension of tectonic setting, check for Pueblo Viejo. Bimodal volcanism, check for Pueblo Viejo, basaltic andesite and dacite. Volcanic domes, check. Volcanic faults, we've got the fault, controlling the intrusion of the domes and the distribution and the emplacement of hydrothermal fluids. Vent proximity, all of these domes were vents. There's evidence that they were eruptive centers before they were filled by domes. We see stacked levels of mineralization, and indeed we see sub-seafloor dissemination placement as that basin subsides and the same volume of rock gets mineralized again and again, producing stacked layers of the paleosurface and stacked layers of VMS beds. So where do we go to explore for these? I want to follow the intraoceanic island arc foliae. Here's its distribution across the northern margin of the Caribbean, taking the Pueblo Viejo model, if you will, and following it across the northern margin of the Caribbean. And sure enough, we don't have to go far before we get to this Viaguana district over here. This is only 50, 60 kilometers away from Pueblo Viejo in exactly the same rock package and in exactly the same stratigraphic position. Here's a geologic map of the Pueblo Viejo, or the Viaguana district. In pink are the dacite porphyry domes. In green are the basalts and basaltic andesites. And in gray are the carbonaceous volcanosedimentary section. I've plotted my Pueblo Viejo map at the same scale to give you an idea of the size of this system here. It's much better. There's a small deposit hosted by the dome already been discovered, but here's where I'd like to focus, is over here in this volcanosedimentary basin. See if I can find the more in Montenegro, but in the Viaguana district. Overlaying the sediments is the same Patillo nearshore limestone as we have Pueblo Viejo. So where do we go? Intraoceanic island arcs, especially island arc foliates, underexplored in general by major mining companies. We tend to focus on calc-alkaline volcanism, calc-alkaline magnetism in exploration for big deposits. I follow the contact between the marginal marine volcanosedimentary section just saw on the previous slide and the underlying island arc. That's a favorable horizon all across the Eastern Dominican Republic. And I've now traced this island arc foliate from Mexico around the Caribbean and south through northern Central America, through Colombia and through Ecuador. Traced the tholeiitic island arc that accreted to the continents, traced and compile all the massive sulfide mineral occurrence. So I'm ready to go. I'm 72 years old and I'm finally ready to go explore. Believe it or not, I've gone and set up a junior mining company in Toronto, and I've got all the groundwork done. All I need now is a corporate sponsor to help me get after it. Just to end here, I want to thank the various mine geologists who I've learned from over the years in the mapping effort and discussions of models. These are people you want to listen to closely. Thanks very much, folks. I'm going to be around after the talk to have a look at the maps.
Thanks for awesome presentation. Excellent. Do you have any questions from the audience? Right in the system.
I think it's that tonalite baffling.
Personally, I don't want to distract from the materials that brought here. Anxious to look at a bunch of them, but we were instructed to bring samples related to skarns and VMS systems, and I'll just point out that over here there's VMS stuff from Greens Creek, as well as some material from the Santa Rita deposit in Mexico. Copper porphyry, not a molybdenum. But the question I had was, and I may have missed it, but What are the most important, lines of evidence that suggest that this is a shallow DMS system?
I think the evidence is strong that the mineralization is coeval both with the domes and with the carbonaceous volcanosedimentary section.
So the domes are suggesting we're not subaqueous.
Well, they intrude rocks that were deposited in the subaqueous setting, but I'm quite confident that the carbonaceous sedimentary section was shallow subaqueous.
Based on what?
Well, it has rooted bivalves in it,
On what?
rooted bivalves. It has shallow water fossil assemblages. It's thinly bedded. As you go up section in the overlying Hatillo limestone, you do eventually get planktonic constituents. But at that contact between the Hatillo limestone and the underlying sedimentary section, it's all very shallow, water. And we have good fossil evidence for shallow water, for a reef environment.
And we can pursue it later. My only comment would be that there are clearly processes that can carry shallow marine features out into deep water. Thank you.
That's a helpful comment. Thank you. Yes.
I have a question. The percolate that you mentioned, but it was also frontier, it's percolate. It was frontier, percolate.
The Bayaguana property that I showed at the end, yeah, that has like that has advanced archaeological grades.
But also be careful about the percolate from metamorphic environment from the lithographia or transfer. Know how to recognize percolate from let's say from porphyry environment or percolate from the process.
Well, first of all, I'm not gonna ever say that there's no hydrothermal porphyry at Pueblo Viejo. There certainly is. But I will say that a lot of the porphyry, particularly a lot of the porphyry in the lithocap, is schistose. It's produced in the Pueblo Viejo. At Bayaguana, there's we're further away. We're outside of the metamorphic halo, so we don't have the complication of a superimposed metamorphic event.
So yeah, it takes from advanced albedo.
I would never say that. Let's call it an evolution of models, and I feel that the model is evolving towards DMS, a big DMS related deposit. And I'll bet anyone who wants a bottle of good wine that the current drill program for a deep porphyry is not going to be successful. My idea is while they're drilling for porphyry at Pueblo Viejo, I'm going to go out and find the next one and chasing those DMS deposits around the margin of the Caribbean and into some northern South America.
Yes, personal problem. For to get job is good. I was working in America. Right, was regional companies. So some of us having theories for foreign receiving. Also, I check on myself about the first day. Some of these there some 2 or 3. But if I get it for foreign, how many people are supporting? Like that moment where everybody was the size small and the rate is okay, but
Yeah,
based on that because
you're quite right. They're true porphyry deposits, like you say, small ones or at least so far they have small in Jamaica. There are also porphyry deposits on the island of Hispaniola, but I've dated them and they're 91 million years, close to the 88 million year dates I got on the calcalcaline rocks at Pueblo Viejo. And they're definitely associated with the calcalcaline magnetism that, that turns on, if you will, in the late Cretaceous. I don't know of any calc-alkaline magnetism in the early Cretaceous in the Los Ranchos Formation. The only fluid inclusion work I've seen is from that paper that I mentioned by Steve Kessler in 1981, 150 down to 100 degrees centigrade. Yes.
In your cross section where you show drill holes going to get crucible depth. I noted that most of those holes, it seemed like the rock down there had several percent pyrite. 2 to 10% pyrite. So what's the origin of all that sulfur? I mean, this is an immense sulfur amount. Where did it all come from?
The ore deposit itself averages 8% sulfide.
So where did all this sulfur?
I think it has to be coming from the magmas that drove the hydrothermal system from that colonitic batholith.
Can you tell something from the isotopic composition of the salt? Seawater or
I think there has been work done on the isotopic composition, and I wouldn't be surprised if it shows a magnetic signature. But I'm not saying there's no magma driving this system. After all, I've mapped volcanic domes. That's telling us there's a big magma underneath, but I think it's a foliatic magma. That we don't have a whole lot of really reliable rules of thumb that we can trust in geology. But if anyone knows of an economic porphyry deposit, an economic porphyry copper deposit associated with foliatic magnetism, I'd like to hear about it.
During the backyard village, I didn't hear you mention alunite. Any other characteristic minerals of that kind of alteration?
There is alunite present, but interestingly enough, it's deeper along the feeder faults. Not so much at shallow. So there is alunite deep in the system. So dates. There are a lot of dates on the alunite, and that was there's a very nice paper by Antonio Rivas that summarizes the argon dating on alunite from Pueblo Viejo, because it's often been cited as evidence for a younger intrusive episode. The dates on alunite run from 40 to 80.
On your slide that showed like the later deeper drilling, there was a really intense number of boreholes in the lower left, or that would be the kind of like the southwest.
Yeah,
Why was that so intensely drilled? Did something get there? Yeah, see that like the bottom of the screen there?
sure.
What occurred there? No, farther down.
Oh, down here?
Right there. What happened?
That's a gossip. That's a gossip. So that's a bunch of shallow drill holes looking for another VMS deposit.
Something wrong there, or I'm not a BNS there.
There is VMS mineralization here. There's a lot. Well, we'll take a look at the maps afterwards, because I've got all the VMSs plotted on the maps. But the entire district has VMS. There are VMS scattered through the entire hydrothermal alteration system.
Call there for questions, and anybody who would like to come up and chat with Carl now, and got the room until 7:30, so free to come up and chat. Ask us. Also get some publications there from SEG. That's probably kind of